Hey everyone, and welcome to your quick, highly effective explainer designed to help you completely master Chapter 4 and absolutely ace your upcoming exam. I am super thrilled to be your guide today. We're going to take all those dense textbook pages and turn them into clear, easy-to-remember concepts. So grab a pen, get comfortable, and let's make sure you score top marks on this topic.
So let's kick things off with a really simple situation. Picture this. You've got a heavy hammer in your hand. You place a tough iron nail on a table and just whack it as hard as you can. Then you do the exact same thing to a piece of coal. What happens? And more importantly, why do these two materials react so incredibly differently to the exact same force?
Well, as you can see right here, when that hammer comes down, the iron nail doesn't shatter. It just changes its shape and flattens out. This everyday observation is actually the master key to unlocking the science of metals and nonmetals. The iron nail is a metal, the coal is a nonmetal, and this simple test reveals the fundamental differences hiding inside their structures. Here is our game plan for this explainer. We've broken the chapter down into 4 manageable chunks: physical properties, chemical reactions, the ultimate showdown, and finally, your exam tips and quick recap. All right, let's jump right into Section 1, Physical Properties, the look and feel of elements.
Okay, our first massive exam keyword is malleability. When that iron nail flattened out under the hammer, that perfectly demonstrated this property. Malleability simply means a material can be beaten into thin sheets without breaking. You've actually seen this in real life tons of times. Think about that shiny silver foil decorating your favorite sweets, or the aluminum foil you use to wrap up your lunch. That is malleability in action, and it's a property almost exclusively owned by metals.
Looking at this comparison, it's pretty clear. On the top row, the iron nail is lustrous, which is just the fancy scientific term for shiny. It's hard and it flattens when hammered. But look at coal on the bottom row. It's dull, relatively soft, and if you hit it, it shatters into a powdery mess. This tells us that nonmetals, like coal, completely lack malleability. Our next highly testable definition is ductility. If malleability is about making flat sheets, ductility is a material's ability to be drawn or stretched out into thin wires. Think about the copper wiring hiding inside your phone charger right now, or the metal strings on an acoustic guitar. Because metals are ductile, we can stretch them out to carry electricity or even create music. Nonmetals? Well, if you tried to stretch a piece of coal or sulfur into a wire, it would just snap instantly.
Now, another crucial point. Metals are absolutely brilliant conductors. Notice the setup on the left. Metals allow heat and electricity to flow right through them with no problem. This is exactly why the cooking pots in your kitchen are made of metals like aluminum or copper. They transfer the heat from the stove straight to your food. But notice the right side. Materials like wood and plastic are poor conductors. That's why the handles of those cooking pots are made of plastic or wood, right? It keeps your hands completely safe from getting burned.
All right, listen up, because this is an absolute exam alert. Teachers just love to test exceptions. We just established that metals are hard solids, right? Well, meet the rule breakers. Sodium and potassium are technically metals, but they are so weirdly soft you can literally slice them with a butter knife in the lab. And mercury? No way is it a solid. It is the only metal on the entire periodic table that exists as a liquid at normal room temperature, which is why it used to be super common in old glass thermometers. Definitely memorize these exceptions. Awesome. Let's transition straight into Section 2, Chemical Reactions, the invisible action in air and water. This is where things get a bit more reactive. You know, when you leave a bike out in the rain for a few days, it gets all covered in rust, right? That is corrosion, which is the gradual deterioration of metal surfaces caused by moisture and air. Rusting is literally just iron corroding. But it's not just iron. Copper turns a chalky green when left exposed, and shiny silver jewelry slowly turns black. It's basically an invisible chemical attack on metals by the atmosphere.
Okay, let's step into the virtual lab for the magnesium experiment. If we take a piece of magnesium metal and burn it in the air, we get this white ash. That ash is a metal oxide. Now, if we dissolve that ash in water and dip a piece of red litmus paper into it, the paper magically turns blue. And this brilliantly illustrates a golden rule you absolutely must write down. Metal oxides are basic in nature. Red to blue means basic. Lock that in. On the flip side, let's see what happens with a nonmetal. Here we have the sulfur experiment. If we burn sulfur powder, it releases a gas. We trap that gas in a glass jar,
Add some water to dissolve it, and this time we test it with blue litmus paper. The result? The blue paper turns red. This proves our second golden rule for the exam. Non-metal oxides are acidic in nature. Remember, blue to red means acidic.
Before we leave the chemistry lab, here is another massive exam alert. Let me introduce you to phosphorus. Phosphorus is a non-metal, but it is dangerously reactive. In fact, if you just leave a piece of phosphorus sitting on a table in normal atmospheric air, it will spontaneously catch fire, all by itself. To stop this from happening, scientists literally have to store phosphorus completely submerged underwater. If you see an exam question asking about a non-metal stored in water, the answer is always phosphorus.
All right, we've gathered all our evidence. Let's head into Section 3, the ultimate showdown, bringing metals and nonmetals head-to-head. I really want you to burn this summary into your memory right now. On the left are metals. They're lustrous, meaning shiny. They're malleable, meaning they can be beaten flat. Ductile, meaning they can be stretched into wire. Plus, they are amazing conductors of heat and electricity, and they form basic oxides. Now, on the right side, the nonmetals, they are the exact opposite. They are dull, they're brittle, meaning they shatter easily, they're poor conductors, and they form acidic oxides. Honestly, if you understand this one comparison, you understand the core of this entire chapter.
But hey, don't let that previous comparison trick you into thinking nonmetals are useless just because they aren't shiny. Look at these everyday survival facts. Nonmetals literally keep us alive. Nitrogen is an essential nonmetal pumped into fertilizers to help our food crops grow. Chlorine is used worldwide to purify drinking water so we don't get sick. And iodine, that's applied as an antiseptic on cuts and wounds in hospitals everywhere. Nonmetals are absolute lifesavers.
And finally, we've made it to Section 4. Exam tips and quick recap. Let's lock in those high-yield revision points so you can walk into that test room with total confidence.
Here is your entire chapter summarized in 5 simple bullet points. Let's run through them together. Point 1. Metals are malleable, ductile, and good conductors. Point 2. Nonmetals are brittle and poor conductors. Point 3. Metal plus oxygen gives you a basic oxide, turning red litmus blue. Point 4. Non-metal plus oxygen gives you an acidic oxide, turning blue litmus red. And point 5, iron exposed to moist air leads to corrosion, which we commonly call rusting. That is the whole chapter right there in a nutshell.
You are officially ready to ace this exam. You've got the structure, the definitions, and those golden rules down perfectly. But before we wrap up this explainer, I want to leave you with a quick thought experiment. You're probably watching this on a phone or a laptop, right? What exact metals are hidden deep inside your smartphone, secretly powering its screen, its battery, and its speakers right now? Keep that scientific curiosity alive, go look it up, and best of luck on your revision. You're going to do absolutely great.